Hi guys, a very warm welcome to this web series which is on machine learning fundamentals and we were on episode 7 and we are today on episode 8 where we'll be exactly starting from the same point where we left last week. We were on decision trees, and in fact we're discussing the concept of uh, Gini impurity, and we were about to take entropy. In fact, I had given one practical example as well using this Gini impurity and using that in decision trees. So that example I had given, and we shall be continuing from the same point where we left. In fact, we were calculating. We learned in the last episode that how Gini impurity is calculated and what it means, what does it mean, and how it is calculated. So let me just go to the same point where we left. If you just see this particular slide which is there, it is on entropy, and in fact before this we had discussed this Gini impurity, and then we had taken two cases: case one, which was a pure node, and case two, which was in fact a mixed node, and which we then designated as highly impure, and in fact. Meaning of the values which we are getting while we in fact evaluated the equation as well. So what is the meaning of different results that we are getting from there? We got it. Today we will be starting at this entropy, and then we'll go on discussing the information gain, which is dependent on the entropy, and then after that I'll be giving you a couple of examples. I want to keep it short so that you don't get bored as well, because these two concepts are there. Some people are feeling that they are little difficult to understand, Gini impurity and entropy, but these are the concepts on the basis of which decision tree actually works. And I am having a good example which will simplify it to a huge extent. First of all, entropy measures the amount of uncertainty or disorder in a node. So, in fact, Gini impurity was different. It was just checking the purity of a node. So, whether a particular node is a pure, or what is the level of impurity in that. So, based on the purity of a node, it used to go to the making a split on those bases. Now, we are having a different measure with entropy, which is again the basis of how a decision tree can split. So this measures the amount of uncertainty or disorder in a node. So it what it answers is how uncertain am I about the class labels in this node. So in fact, the Gini impurity was saying how much certain about am I about the purity of the node. That means how pure it is. So this is about how uncertain am I about the class labels in this node. Entropy comes from information theory. So this entropy is coming from information theory. So what we are going to understand, and in fact in a deeper manner we are going to open it up. Entropy equals, if we have to evaluate the formula for entropy, it equals minus summation of pi log 2 pi. So this pi, it will be number of occurrences which are there. So number of choices that we are having, cases which we are having. For example, we are taking the example of the students which are there. So in case of students, a student can be either pass, or a student can be fail when we are doing in fact the categorization there. So entropy in that case would be equal to minus P1 log 2 P1 plus P2 log 2 P2, because it is these are the two cases which are there. Now if a student is pass, it is going to be 1. If a student is fail, is going to be 0. And we know the value of log 2 1 is equivalent to 0. So log 1 is going to be 0. So entropy equals minus 1 log 2 1 plus 0. So definitely this entropy here will be reduced, or the value which will be coming for this one is going to be 0, because we have simply evaluated it. If you can just see, it's on your screen. we are giving the substituting the value of log 2 1, that is 0, and then when we multiply 0 with the 1, it will become 0. 0 plus 0 is 0. So it is entropy will be equivalent to 0. And what does it mean when the entropy is 0? Entropy 0 means no uncertainty. There is no uncertainty whatsoever. That means we can go ahead with, if lesser the entropy, that means uncertainty is less. More increased entropy, that means uncertainty is more. Now we can take one more case where it is a mixed node. So here it was a pure node where all students are pass. So P pass is equal to 1, P fail is equal to 0. Now here it is a case where number of passes are 5 and number of fails are also 5. So P pass is equal to 0.5 and P fail is equal to 0.5 because equal number of passes and fails are there. Now what will be the value of entropy? So we have to substitute these values exactly in the same manner we did in the previous example. So with this one we are getting entropy is 1. That means it's maximum mixed mode. Maximum entropy in binary classification occurs when classes are equally mixed. So there is an equal mix of classes. Then we are having a maximum entropy, that is 1. So lower entropy means more purity. Higher entropy means more uncertainty. There will be a mixed class. The tree prefers splitting that reduces entropy the most. Though the tree will prefer to split the nodes in such a way so that entropy will be reduced. It will be lesser. So when it is lesser, it will be dividing in such a way. So if you just see now this decision tree, we are giving the same example, which is student performance. If the student has studied for more than 5.5 hours, if it is yes, the leaf node will be, that means it will be giving a decision. So leaf node is coming as pass. So it will be giving a decision that it is, if a student has studied for more than 5.5 hours. But if that is not the case, then it will be recalculating the impurity. So how it will recalculate? Is attendance greater than 70? Now based on how the segregation will be happening. So which particular, this one, that will be either decided by Gini impurity or it will be based on entropy. One of the two. Because in a decision tree, it will be either taking, we will be giving a variation or mechanism that, it will be Gini impurity, it will be going through that, or it can be in fact the entropy. So I'll be showing you both the examples in fact. So we recalculate this. Is attendance greater than 70? If yes, if no, then it's simply going to fail. If yes, then it will again recalculate the impurity. So impurity in this sense, it is using Gini impurity. So is assignment score greater than 60? If no, then it will directly fail. If yes, again recalculate impurity. Is midterm exam marks greater than 65? If yes, it will pass. If no, it will fail. So here it is finishing it off. It is not going further because this is the 4th level. So it is just calculating it at, for example, the depth of a tree is equivalent to 4. So 4 levels deep, it is not going beyond that. So that is how this gets calculated, and it will be either application of Gini and Gini impurity, or it will be entropy, one of these two, on the basis of which it will be going. Definition of information gain, first of all. So information gain is one more concept. In fact, 3 of these we had explained little bit in the earlier video which was there. That is episode 7. Information gain tells us how much uncertainty is reduced after a split. How much we are having reduced uncertainty after a split happens. So we should be getting information gain to whatever extent it should be. The information gain should be happening. It is based on entropy. So information gain, if we have to calculate, how to calculate that, it is equivalent to entropy of the parent node, then weighted entropy of children, the child nodes which are there, or the child node which is there. So it is weighted entropy of that. So the tree asks, after splitting the node, how much disorder have I removed? So when I splitted the tree, when I splitted the node, how much disorder have I removed? the feature with the highest information gain is chosen. So wherever you are having a highest information gain, that particular feature will be opted for. Why weighted entropy? So why we are choosing weighted entropy there, and that is coming in information gain? Because child nodes may contain different number of samples. A siblet producing one large child node, one tiny child node must account for node sizes fairly. So weighted entropy is equal to n left divided by n entropy left plus n right divided by n entropy right. What does this mean? We'll be evaluating with the value. So numerical example. For example, you are having a parent node that has 10 students. 6 are pass, 4 are fail. We have to calculate entropy for the parent first of all. So parent entropy is equivalent to P pass equals 0.6 is 60%. So out of 10, 6 is 60%. So it will be 0.6. P fail and then equals 0.4. So this is entropy parent will be equivalent to minus, if we are putting the same formula of entropy which we have seen up there, you have to calculate the entropy. So it will be 0.6 log 2 0.6 again, because that was P1 log 2 P1 and then log P2 log 2 P2. That is the formula. So we are having two cases here. So 0.6 into log 2 0.6 plus 0.4 second one, which is 40%, 0.4 log 2 0.4. If we are evaluating this, the value is coming 0.971. This is a simple mathematics which is done there. So you'll see that value. This is the parent entropy of the example where we are having 10 students. Now suppose we are splitting, left child is getting 4 pass. Now when we split this, left child is getting 4 pass, 1 fail. Right child, that means the right node, when we divided it, right is getting 2 pass, 3 fail. We have to calculate the entropy of left child now. So how to calculate it? It is very simple. Entropy left is equivalent to 0. Because it is 80%. Out of 5, if 4 people have passed, that means 80% have passed. And 1 person has failed, that means 20% has failed. Right? So entropy left is equal to 0 minus 0.8 log 2 0.8 plus 0.2 log 2 0.2. When we evaluate this, this comes to be 0.7722. So entropy left is coming 0.722. Entropy right with the same logic, evaluating in the same manner, is coming 0.971. What does that mean? Weighted entropy after split, both child nodes have 5 samples each. That is correct. Now what is weighted entropy? Weighted entropy will be 5 by 10 into 0.722 plus 5 by 10 into 0.971, because 0.722 is the entropy of the left one, 0.971 is the entropy of the right one. So weighted entropy we evaluated, weighted entropy is 0.847. This is what we got from the child nodes. Now, has the information gain happened? That will be evaluated when we will be saying information gain. So we have seen here information gain is equivalent to entropy parent minus weighted entropy of the children. Okay. So if we put the same values here, information gain is equivalent to entropy of the parent, which is 0.971 in our case. And then we are negating it with weighted entropy of the children, that is weighted entropy calculated from the children, that is 0.847. So our information gain is 0.124. That means definitely this split which has taken place, so this split reduces uncertainty by 0.124, or we can say information gain is 0.124. The tree will compare this with other possible splits. So this will be again compared with, so internally what is happening. So this is the concept actually, what happens when we are putting it with entropy, what exactly happens, how this information gain is calculated by, you don't have to do it anyways. It is done by the algorithm itself. This decision tree will be doing it internally and then taking the decision if you are putting the variation as entropy, or for example, you are putting it as Gini impurity, so it will be calculating that way. So on the basis of this, it will be checking all possible splits and it will go with that kind of a split which will be having highest information gain. This is what is their Gini impurity difference, measures impurity directly, computationally simpler, faster, default in scikit-learn, so it is available there. Entropy is it measures uncertainty using logarithms used with information gain, slightly slower compared to Gini impurity. It's more theoretical information theoretic interpretation. In practice, both often give similar results. So what we have observed, or you can just see as well yourself, whether you are using a variation of Gini impurity or you are using entropy, you will just observe that results which are at the end achieved from a particular this, it will be same. When we are putting the Gini impurity, the criterion which is there, the criterion which we are giving, so how we are defining it, the criterion meaning whether it can be Gini, or it can be Gini impurity, or it can be the other one, which is entropy. So from sklearn.tree import decision tree classifier, that is right, this is the algorithm which we are using. Model is equal to decision tree classifier. We are putting criterion, so this is a skeleton which will be used in fact while we are explaining or defining this decision tree, and that we have done already. In fact, this particular thing we have done with the previous example, couple of examples. Then we are saying maximum depth is equal to 4, so maximum number of repetitions or trees or nodes, number of subnodes it will be creating, it will be going to the depth of 4, which we have seen here in this one as well. So this is a depth of 4, 1, 2, 3 and 4. So it will be going maximum to that particular level, and the random state we had been doing it from the beginning in various other algorithms as well. So it will be just maintaining that output, so that it will be giving a similar kind of this one. So that random state we are putting, it's by convention, it's 42. Meaning criterion is equal to Gini, tells the tree use Gini impurity to evaluate siblets. To evaluate siblets, the tree will choose the siblet that gives the lowest weighted impurity. So when we are saying this code which is on your screen now, we are telling with the criterion that you have to use Gini impurity. We are telling this to decision tree classifier, which is the algorithm. When we are saying criterion is equal to Gini, so when we are saying criterion is equal to entropy, so at that time, I don't know, I don't think this is reflected here. So this has to be, in fact, criterion is equivalent to entropy here. So it has to be entropy. When we are saying that, at that time we are saying that you have to use a criterion entropy, tells the tree that use entropy, calculate information gain. The tree will choose the siblet with the highest information gain. So these are the two differences which are there. And I think the code which is written here is by mistake. Criterion should be the entropy. So anyways, that is not a big thing. I can just show it to you on this as well, directly taking to Python. So what is the summary of this? Gini impurity and impurity measure used to choose good siblets, entropy uncertain measures used before and after splitting, and information gain reduction in entropy after a siblet. And in Python, we are having now, it's showing here, criterion is equal to Gini or criterion is equal to entropy. These are the two variations which we are having. And then if we have to compare it with the previous algorithms, you can just see model type will be mathematical equation in case of regression models. Decision tree, it will be rule based. Relationship will be linear assumptions. Non-linear in decision trees. Interpretability is moderate complexity. But there's a high clarity as far as decision trees are concerned, and that we have witnessed ourselves as well. So this is in fact, this was a purely theoretical kind of a thing, but I will not leave you before just showing you that this decision tree using entropy is there. But I would like to just give a little bit of a clarification or definition here before I can just. This is the same code we had written earlier. This is the one which we had written earlier. In episode 7, I have explained it line by line. So this is the same code here as well, just there is one difference. First of all, we are choosing the model Gini here with the decision tree classifier, and then criterion we are saying Gini here, and then second one we are putting as entropy. So we are using two models, both the models here, and then we can get a comparison of them as well. So we are putting Gini, we are putting entropy, so they have been done here. And then model entropy fits x underscore train and y underscore train. In the same manner, we'll be doing it for the Gini as well. That Gini underscore this. So for Gini as well, we are putting the we're putting this model, and then we will be just plotting. So it will be giving us two separate things for one for entropy, and one will be for the Gini. So I can just show you the output of this program as well, so that it will be a little more clear. This is the same program we had written earlier, which has generated that graphs. If you remember, two graphs are there. So first one is this. So if you just see, uh, this is Gini impurity, and it is exactly the same values I believe were there for the previous program as well. So this is generating these values. What kind of things are there? It will be giving how many samples were total values, which value which we have given, and we have tested. We wanted to test it whether it was a pass or a fail. So that is this, and then there is one more which will be doing it with entropy. So if I close this one, there is one more which has been generated. So that is this one. Let me just pull it to this particular screen so that you can see. So now it's a decision tree using entropy, and it is also showing the same thing. What is the entropy value? So samples, how many? So samples and all, everything is same. Just few things have changed. That is, instead of entropy. And if you see the result, overall result of this as well, when prediction comes into picture, if we have, it will be giving, both of these will be giving the similar values. There is nothing much of a difference as far as the results are concerned. But you should be understanding this, because we'll be taking random forest next. A random forest is combination of these decision trees. There can be multiple decision trees are there. Until unless this foundational concept of entropy, Gini impurity, entropy, and information gain is there. The logic of a particular algorithm, how it is working, how it is taking a decision, how it's splitting the node into two, and how it reaches to that particular conclusion. There's a logic behind that, and entropy and Gini impurity are the two things, two criterions, you can just say, on the basis of which it is splitting the node. And this has to be clear in your minds, so that we are ready for the for taking advanced algorithms. I have wrapped this little faster. I'll be just because I wanted to just convey in this one what comparison of entropy and Gini impurity. Gini impurity we had taken mathematically last uh, episode. In this episode, I wanted to just wrap very quickly entropy and mathematical equation for that, and show you the practical model where both of them are there. Although I have not written it in front of you, it was written program which I have showcased, but all of this code which is there, I have explained it in the previous program line by line. Just to, one addition which has happened is, in addition to Gini impurity, we have included a code for the entropy as well, and we have seen that results are similar. But I will be putting one more program with this decision tree in practical before we can go to next major concept which will be there. That will be in fact a random forest. And so random forest classifier which is there, that will be taken as a major concept next. But before we go there, there will be an episode which will be taking one example, or it will be a part of the same episode, if not separate. Initially, first of all, a program which will be talking in a meticulous way, again, about implementation of decision tree classifier with both entropy and this Gini impurity, and maybe possibly giving a little bit of a comparison as well, which was in fact seen here also. So until then, thank you so much for connecting, and you please subscribe to the channel if you feel that this is giving some benefit to you. I'm trying, it is basically the fundamentals of machine learning, that is true, but one thing always, as a teacher as well in higher education, I had always aspired. I don't encourage students to just for grades and marks. I always encourage them for educational excellence, and that will be achieved only when we are going to the core. uh, it does not matter how one teaches, and definitely I cannot do anything as far as I with my 21, 22 years of this teaching experience. What I have realized and learned, that a teacher will not be able to do much. Just a bit of an inspiration for a student, that is it. There's hardly anything worth learning that can be taught. So definitely teacher is not able to will not be able to do much, but definitely an inspiration. So my inspiration, and for my students and for anybody who will be taking any benefit through these virtual channels as well, is just one thing, that you have to help your own self. And I can just or it's somebody can just inspire you. The real learning will be happening from your own self. So you have to just do it. And that's why I am just concentrating more on the core of something. It should not be that we are showing something else, and then internally we are not aware about the basic concepts. So when it comes to, for example, algorithms, somebody might be doing a lot of other algorithms which are there in machine learning, but the basic concept which is there, that might be missing. So that should not be there. So that fundamental concepts which are there. So this decision tree is based on certain fundamental concepts. So first of all, we need to explain, understand, comprehend that, and then only we can just go ahead with advanced concepts which are there. So that is something very important, and I felt that this should be like this. And in fact, for the future concepts as well, wherever I feel that it is important to focus on a particular concept, so I'll be doing that, and then I'll be moving forward with the rest of the concepts there. So thank you so much for joining this session, and do subscribe to the channel if you're feeling that this is beneficial for you. Give us your critical comments whatsoever, so that we can improve for the future recordings as well. Thank you so much once again for joining.